Oh, well. Okay, so let's start the STL overview. So among all the STL features, I will talk about container, focus on container, allocator, iterators, and then there will be the tuple and an example with the tuple. There will be an exercise with the allocator and an exercise with the tuple. So the material, so I had these slides in our presentation. So the code is in code STL, all the snippets that I present. So as usual, you can while I talk, you can try it out. And the exercises are in exercises STL. So STL has a lot of things inside. Many of them we didn't even talk about, and some of them are not really interesting for HPC, and it depends. It really depends on the domain of every developer. So focus on containers, iterators, and algorithms, and tuple. So the first container we consider is the SCD array. You saw it already in several code snippets. So it's like a C array. There's no overhead with respect to a C array. It has a static size like the C array, and it has a method at for accessing, which gives you an error at runtime if you're accessing out of bound. While if you have the square bracket operator, it's undefined. You can get segfault, or you can get simply nothing, the wrong result. Then it has constant time access. If you swap two arrays, it makes a deep copy of them. While for all the other containers, it just exchanges the pointer. You can see here the syntax. So it can be const-text constructed. So it's the only container which can be constructed with const-text, and it's allocated on the heap, while the other containers by default have an allocator template parameters which allocate on by default on the heap. Sorry, this is on the stack. Did I say the heap? Yeah. So it's allocated on the stack, while normally containers are allocated on the heap. So you can query with get, like with the tuple, and that's members size, back returns the last element, and front first, and so on. So second very common container is the STD vector. This is the most used container for most of the time. What you will need is an STL vector, and so it's resizable, which this is already the first difference with respect to the array, and it's fast for pushing and popping elements at the end. It is guaranteed to be contiguous in memory, like the array. So it has constant time access wherever in the array, in the vector, but it's expensive to resize, because if you change the size, it might be allocating a new buffer in memory and copy everything buffer. So you can use capacity to query the capacity of the vector. For instance, here you see in this, you can try to compile this file. You see that here I define a vector size 2001. Then I query its capacity is 2001. I push back something. Now the capacity is doubled. So why? I just pushed one element. So this is because it has a compiler-dependent policy to allocate the memory. So it says Allocating memory is expensive. I have to allocate a new buffer and copy everything in the new buffer. So I do it once, and then I don't want to do it very often. So it just doubles the size as a policy. This is GCC. Other compilers do other things. So this is not standard. Then there's a shrink to, which is non-binding, meaning that the standard doesn't say that this is up to the compiler whether it really implements what you want to do, and this should be it should shrink the storage to the real size needed. So in this case, 2002, because I had 2001 and I did a pushback of 1 in 2002. Then what is very useful is this reserve. So reserve can avoid the reallocation. So if you know beforehand how big will be your vector, so use reserve of this number of elements, and you won't need it won't be a reallocate. It won't be. So if you do reserve 2004 and then you push back 1, it doesn't allocate another buffer and copy everything. So it just use this buffer because it has some extra padding at the end. So the structure of bool is specific. So it has a specific implementation. For optimizations, it can be that the booleans are stored. Several booleans are stored in a single byte, for instance. But this depends on the implementation. So it's not defined in the standard. And usually it's not good practice using standard vector of bool because there's, for instance, there's a bit set. If you know, so the vector of bool is a vector. You can work with iterators on it. You can traverse it with iterators. It allocates on the heap. And while the standard bit is an array of bit. And if the only thing is that it has a static size. So you have to know the size beforehand. So here in this example, I define a standard vector of bool and a standard bit set, which are the same. So true, false, true, and this is 1, 0, 1. Then I query the size of both to see how much the size of returns, and I query the last element of the last bit. So what we get? Here we get 3, that's normal. Here we get 40 and 8. So why there's a difference in the size? That's because B, which is the vector of bool, it doesn't contain the real storage, the real things getting stored. It contains a pointer, and the real data is on the heap. Is being allocated on the heap, while the bit set, it's one. It has a size of 1 int, so 8 bytes, and it has the first bit set to 1 and the rest set to 0. So if you increase the vector of bool, no matter how many bool you put there, it will always be size 40 because it contains a pointer to the real data, while the bit set really contains the bits that you are allocating. So DEQ
mentioned the fact that when you access with a square bracket operator a vector, you get the reference to an element. In the case of vector of bool, you don't get the reference to a boolean. You get the value back. Okay? You cannot access. You don't have a reference at the end. So
you cannot access references, and also it's not guaranteed to be thread safe. So if you have 2 threads accessing 2 different elements, you might fall into a race condition because these 2 elements might be in a single byte. So this is depending on the implementation of the SED vector of Boole. So SED-DQ is a double-ended queue. It's similar to SED vector, but it's fast also to insert at the beginning. So not pushing and popping at the end, but also at the beginning. It is not necessarily contiguous in memory. It is contiguous in memory, but then if you add something at the front, at the beginning, then it might allocate another buffer in another place. So now we can compare the efficiency of a standard vector to a standard DQ. So we can compare. We have these two files on the repo. So we can try to. So timing them. So for the DQ, I get half a second, more or less. Right now, I try with the vector versus DQ. I get a little bit, but not a big difference. So this is for pushback. So for pushback, they're both quite efficient. But so here I have a huge container, and I'm pushing back in this huge container amount of things. So it's just almost reaches the limit of the number representation for integers. So now what if I start to insert at the beginning instead of at the end? So we can modify DQ. So here we just uncomment this one. And I do the same thing for the vector. So here I was setting 10 to the 5th instead of 10. But now you will see that just G++. So here we can keep waiting, and so I will just stop it for 6 seconds. And while the DQ, so this has the same performance as before, roughly. So you should not always use vector, depending on what you have to do. If you have to insert things at the beginning. So the vector, every time you insert at the beginning, has to either, in the case scenario, it has to move all the part after the point of insertion. It has to shift it, or if it exceeds his capacity, allocate a new buffer and copy everything. While the DQ is faster. Okay, so ForwardList is another container. This is a linked list. We have an element and a pointer, and the pointer element. And these elements they're not necessarily contiguous in memory. So it's efficient in inserting or removing anywhere in the list. It does that in constant time, because it just to remove and to change the pointer. So if you want to remove this one, I just change this pointer. This is done in constant time, whatever. It doesn't matter where in the list this is. So it has slow random access because if I want to access in the middle, I have to do all the hops to a right there to follow the pointers. So it's linear. And STD list is like the forward list, but has the two pointers, one going backward and the other one going forward. So now we can compare performance with respect to vector. So if I compile, so I compile the list example. Here I cannot use the same syntax for the two things, and this will be clearer later on when I talk about iteration invalidation. Then I will explain why these two things are different. So this takes almost nothing, and now vector versus list. So this takes definitely more. This because the same reason as before. If I'm inserting in the vector, then I have to move after the point of insertion, the best case scenario. So use the list when you're inserting or removing in the middle of a container. When the containers are large, because if the container is large, if I have to move it, it costs a lot. So if I'm inserting in the middle of a large container, a big chunk of memory. Or when the element size is big. If I have big elements which are memory, to move them is costly. So maybe I want to use a list. 90% of the cases, vector will be more performant than the list. But there are some cases in which you want to use a list. So there's other containers like queue, stack, and priority queue, which are container adapters. It means that they have a template parameters in which you specify another container. So they're just implemented using other containers. And you can choose which container you want to use based on your application. So these are standard queue implements the first in, first out policy. So you push into one end and pull from the other end. Stack is first in, last out. And priority queue is an ordered container when you get the largest value in constant time. Then there are the associative containers. These are map and set, and then multi-map and multi-set. So there are two versions, one pre-C++, one which is still the default one, in which insertion removal is in logarithmic time. These are normally implemented with the binary tree algorithms. And there's an ordered version in C++ 11 which are implemented with another algorithm. And the search insertion removal is in average constant time. So if you have a small container, probably the first one is faster. If the container is large, it might be more advantageous to use the second one. So here's an example. So you see you have a map. So So this is how the map works. I have a key as first argument. So in this case, it's a string, and let's say double. Then I insert in the map I insert pairs in the map, which are key and value. I can specify the same keys, but then this will be filtered out in the standard map. So the size will be 3 in this case, because I insert two things with the same key. If I use multi-map, this size will be 4, and both of them will be stored inside the map. Set is very similar. It's just like a map where the key is the value, and I can insert. I have, for instance, a set of doubles. I insert twice the same value, and I get size 2. And if I have multi-set, the size will be 3. And this this define returns an iterator in both cases. There's also other ways to access to query by keys. So they should not use in performance critical regions. Normally the queue or vector are efficient for the performance critical part. Inplace, so is a way to insert in a container. So these were all the containers in the standard library. Now we're talking about other APIs. So the signature of Inplace is this one. So it accepts an iterator and arguments. And what it does is that it inserts a new element in the iterator before pause, and it constructs it in place, passing these arguments to it. So let's say that this class, my class, where I define a copy constructor and a constructor with side effects. The only things they do, they print out copy and construct. So I run this code. What would you? It's printed here. So you can try to run it in the example. So here there will be construct and a copy. Construct because I'm explicitly calling the constructor, and because to push back I'm doing a copy in the inside container.
Why wouldn't it move?
Yeah, the thing will come. You can. There's a way to do a move. I think that with pushback it does the copy automatic. I don't know if I implement the move constructor. Maybe it's called the move constructor if it's implemented.
Yeah, it should be moved in this case because it's a temporary object created there.
Yeah. So,
I think so.
Yeah, in case there's a.
Yeah, there is an overload for pushback with our value reference.
Yeah. So if in this case there's a copy constructor and there's no move constructor, so it's copied. If I implement a move constructor, then it will be construct and move. While if I Inplace, then it's only calling the constructor, and it's constructed directly in the last position of the container. So you can do it. So now, this is a question for you. So what would you expect? What would you expect these to print? So we saw that Inplace back prints construct because it constructed in place. So if I Inplace at the beginning instead of at the end, what will this print? I have to modify it first. So any idea? Anyone wants to guess? Okay, let's just see. So it prints construct, copy, and construct. So why does it be then? That's because this is a standard vector. So I put something in the vector, and then I put something before at the front in the vector, so it has to move the element which I of one position. So it has to do one copy. So it calls a copy constructor.
So if you had like, if your vector one element will be 100 elements, will be 100 copies. Because you have to move all of them.
Yeah. If I push back, if I do this 100 times, but if I do reserve 100, no, because the length is. I mean, if I do, it depends on the size, not on the capacity. Say.
Oh, okay. Well, we'll have to try doing a copy of each element, because it has to shift all the elements, has to copy one by one, or if it's doing a mem copy, in that case, it doesn't have to do the construction.
Okay.
I have no idea.
It does a move assignment. Yeah. I picked once in the implementation of GCC.
Okay. Okay. So, allocator. So, almost all STL containers have an allocator. One which doesn't have an allocator template parameter is the array, which is allocated on the stack usually. So this can be used to implement your own allocation, deallocation, and to, for instance, if you have specific memories, or you want to implement a vector for a specific type of memory, and this often could happen in high performance computing, want to allocate on some memory which is you have several memory hierarchy. So you can implement your own allocator. Since C++11, the API to do that is extremely simplified with respect to C++03. And there's also the guarantee in the standard that the allocator, there's a one copy of the allocator instance in every container, so that you can have a stateful allocator. So now this is an example of an allocator, a stateless allocator. You can allocate up to 100 elements, and then it will throw bad alloc. And the allocate method, so you have to do this type def to implement an allocate and a deallocate method. And it's all what is strictly required by the API. So if you do this, then you can pass this struct as allocator template parameter. So in this case, the allocate does a malloc, so it allocates on the heap. And yeah, the deallocate does a free. So now, the question is, as an exercise, is how would you do an allocator modifying this allocator on the heap to make it allocate on the stack instead? So let's say that we fix the size of the thing that we want to allocate to 100. We want to allocate a vector of 100 elements on the stack, which is kind of stupid example, but okay, it might be. We don't have any other type of memories. So if you would have a device and you would want to allocate on the device memory and define an allocator which allocates there, then you would face a similar problem. So we can leave. So you can find this. You can look it in this folder for the exercise. You can leave 10 minutes, 15 minutes.